So our next presenter is Mr. Mohamed Zemzem from the University of Montreal. His presentation will be the thermal insulation capacity of cold protective clothing materials in extreme environmental conditions. So yes, I can see your screen and the floor is yours, Mr. Mohamed.
Perfect. Thank you very much for the introduction, and just give me 1 second to be sure that I can. Is it shared my screen?
You're sharing your screen, but it's not in full screen, in full screen mode. So if you want to make it full screen mode.
So is that?
No,
just to be sure.
Yeah, so we're seeing your slide, but we're not seeing them in full screen mode. So
okay,
if it's okay for you, you can go one slide after. Oh, now it's going. Okay,
That's
perfect. Thank you.
Perfect. So hi everyone, and thank you for taking the time to attend my presentation. And I would also like to thank the organizing committee for inviting me to speak. As already introduced, the topic of this presentation will be about the assessment of thermal insulation capacity of textile assemblies used for making cold protective clothing, and that in the presence of extreme weather and environmental conditions. This project was realized in collaboration with Logistic Unicorp company, to whom I address my thanks. So first of all, let's start by putting the subject in the context. People working outdoor in winter experience cold stress for large part of their shift. And a recent study revealed 10 jobs for which workers are subjected to temperatures that can drop to minus 39 degrees Celsius. So as you surely know, thermal stress can have harmful effects on performance and health of the human body. Hence the role of cold weather clothing in maintaining the user's thermal balance despite variations in weather conditions and metabolic fluctuation. So the present work aims for adapting thermal measuring methods to be applied to extreme weather conditions and try to assess the influence of environmental conditions on thermal insulation efficiency of textile assemblies used for making cold weather clothing. To do so, 3 technical textile assemblies that we named ACA, DCA, and DPG are used for this study. Each assembly is composed of 3 layers of non-woven insulating materials sandwiched between 2 protective fabrics, as you see in the figure. And these assemblies are made in a way that we use 2 different insulating materials as well as 2 assembling configurations. So on the other hand, the evaluation or the assessment of thermal insulation properties was performed by a guarded hot plate device, commonly known as skin model. The skin model simulates the heat transfer from the body surface, represented by the red box in here, in this illustration, through clothing layers up to the environment. And this measures the thermal resistance of the textile. From the other side, the upper side, the effect of 3 parameters are to be assessed, which are ambient temperature, humidity, and wind speed. A wind simulated by an airflow perpendicular to the sample surface. So first, the total thermal resistance measurements were performed over a temperature range going from minus 40 to plus 30 degrees Celsius at a step of 10 degrees. And second, we assessed the effect of specific humidity between 5 and 20 grams per kilogram of dry air. Here we are talking about humidity at positive temperatures. And finally, as may be seen in this video to the right, the influence of wind on the thermal resistance is assessed through a wind blower with a square opening at the outlet. So this setup generates an airflow perpendicular to the surface of the sample, and the fan ensures an average wind speed of up to 42 kilometers per hour. Let's jump right away to the results and start by taking a look at the effect of temperature as well as the configuration of the assemblies on the total thermal insulation. The histogram shows thermal insulation results for the 3 assemblies at temperatures ranging from -40 to 30 degrees Celsius. That's with no wind speed. The wind speed is 0. It can be noted that the RCT of the DPG assembly is higher than that of the other 2 assemblies at all temperatures. And although DPG assembly is thinner than the others at equivalent weight, obviously it has better thermal insulation, and this is due to the nature of the insulator put inside of our assembly. And for the histogram, it can be seen that within standard deviations, let's say, the results presented do not allow us to conclude that there is a significant effect of temperature on the thermal resistance in studied range. Let's move to evaluate the influence of specific humidity. This figure represents the main effect plot of humidity on the thermal insulation as generated by our experiment. And the results show slight increase in RCT with increasing specific humidity in air from 5 to 20 grams per kilogram. And the third parameter, which is it's more interesting to see, is the wind speed. Here again, we show results of one of the assemblies, which is ACA. The following figure represents the variation of thermal insulation of the assembly as a function of 3 wind speeds, 0, 4, and 16 kilometers per hour, and range between -40 and 30. And now, if we compare the 3 grades of blue that corresponds to different wind speeds, we can observe that an airflow oriented vertically to the sample affects the thermal insulation. So RCT of 3 textiles drops to less than 15% of their initial value only by the presence of an average wind of 16 kilometers an hour. So also we noted that this effect of the wind is independent on any variation of ambient temperature or humidity. So for the results presented in the previous section, it can be concluded that the wind speed is the most influential parameter. And several factors and mechanisms can be reason for this, namely the pumping effect caused by the compression under wind, the air permeability of the assemblies, as well as the presence of seam in the fabric. Needed to keep all assemblies part together. So in the upcoming slides, I will take some time to go investigate further each one of these aspects. We start with the effect of compression on thermal insulation. So to identify this effect, the RCT of the tested assembly is compared to that of an incompressible rigid extruded polystyrene pump, has been chosen to be the closest thermally and to our text. Wind speed is then assessed at 0 and 23 kilometers an hour. At 0 wind speed, the thickness and thermal resistance of the textile and the panel are comparable. But at 23 kilometers an hour, a significant difference is observed. In fact, RCT of the textile assembly decreased by almost 90% compared to the rigid panel. This brings us to the second aspect. So in order to determine the effect of air permeability on RCT, an impermeable film, as shown here in this figure, is put on the outer side of the protective fabric, and film is chosen so that its thermal insulation is negligible. So by memory, it was 0.2 chlor or something. And the results in this histogram show thermal insulation of our 3 assemblies at 0 and 16 kilometers an hour. We can see the drop. In RCT shown earlier. So over the addition of film on the top of the assemblies at 16 kilometers per hour, we can clearly notice a substantial recovery. ACA, for example, RCT increased from 1 to around 6 chlor only by adding the impermeable film. So in fact, this is understandable since air penetration through the fabric and the insulators leaves room for air to circulate, which increases convective heat exchange and reduces thermal resistance. So a quick look at the outer protective tissue in our assemblies by SEM shows clearly here in circle cavities through which the air could easily penetrate. Third and final aspect is sewing effect. So we noted that the presence of the seams caused by localized compression at the spots where the thread passes, like the circle in pink in here. This compression reduces the thickness of the structure and increases the effective thermal conductivity of the insulating part. So we start again from thermal insulation data at 0 and 16 kilometers per hour for our 3 assemblies. And next to them, we add data associated to the same assemblies, but without sewing, no seams. So we can notice the increase in RCT for all assemblies with and without wind. Thermal insulation of SEA, for example, increased from 6 and CLO over 80%. Let's recap. Wind significantly affects the thermal insulation regardless of the nature of the insulation and the type of assembly. RCT of all studied assemblies drops by more than like 85% only by the presence of an average wind of 16 kilometers an hour. Different mechanisms contributed to this thermal loss, such as compression, air permeability, sewing, so on. And RCT increased slightly with the increasing specific humidity in the environment, but no considerable effect of temperature. And at the end, I would like to express my gratitude and appreciation to my tax program who funded this group for providing all equipment and technical expertise. And
thank you so much, Mr. Mohamed. Very interesting study. Is there any question from the audience to Mr. Mohamed? Oh, Rashid. Yeah, go ahead, Rashid.
Hello, Mohamed. Thank you.
Hi,
it was a great presentation. I really like it. I have a question for you. So why are you able to estimate the temperature, how much it can sustain in the extreme winter condition?
Just please repeat the question. I didn't get it.
So why are you able to estimate the temperature for the clothing for the extreme winter environment, like it will be able to sustain like -20 or -30 degrees, something like that?
Yes, we were able to assess the effect, but the problem there is no effect. So usually in the standards they do in regular and ambient temperature, but when we tried it in environmental chamber from -40 to 30 degrees Celsius and assessed the thermal loss of our assemblies for all of them, for 3 of them, we didn't notice any variation, any effect of this temperature on the thermal resistance of our material.
Thank you.
You're welcome.
Do we have any other question for Mr. Mohamed? Okay, thank you so much again for your presentation and
You're
participating
welcome.
in the ITS Symposium in the students section.
Thank you for organizing such a good, wonderful event. Thank you very much.
Thank you. So I think, well, right now we have our chat room, so everyone is welcome to join the chat room you want. You can pop in and pop out through different chat rooms. And yeah, so thank you so much. I don't know, Dr. Patricia.
Yes, so just so we have 3 chat rooms. We have one chat room with Courtney, then we have one chat room with Sine, and then we have one chat room for us for the ITS. So if you want to learn more about the Institute of Textile Science, so we're going to open the chat rooms right away as soon as we close this main room. And then we'll have then a pause, and then we will see you again at 10:30 Monday time, 12:30 Eastern time for the following session on next generation of PP. So see you very soon. And thanks again for everybody. This was very interesting.
Thanks, Patricia.
Thank you.